we're going to pick off from last time, and then I just put in red the kind of the backup plan in case anything goes wrong, but I think everything should be resolved. I know that I have the updated version of Zoom, so good. Okay, so today's plan is to basically start from chapter 3.2. So we already kind of covered 3.1, but I'm going to start by reviewing just the highlights of where we left off last time. So where were we at? The first thing, I guess the last equation that we wrote down was essentially the total charge. So we had this quantity Q plus, and this was equal to 1 over 8 pi g times an integral at scribe plus minus of terms that we introduced before. So we had 2 bonding mass F plus U over 2 dAya, and then YA and A. Okay. So basically what we had in last time is that we pointed out that these guys were appearing in our metric expansion of large R, and that these terms were basically the parameters for our diffeomorphisms. And so right now, this whole quantity is defined in terms of the boundary data, which is the past limit of future null infinity. So I'll just draw that Penrose diagram so that we have that in mind. We found that there was a boundary of Minkowski space was null. So we had basically a future null boundary and a past null boundary, and this was parameterized by coordinate u, and we went to large R. And basically now this charge is as if I had a Cauchy slice that is hugging future null infinity and ending at what I call scry plus minus, which is this u goes to negative infinity limit. Great. So we have this quantity, and then our goal is going to be basically to show that there's a ward identity. And by a ward identity, I mean the following, is that we're going to want to show that if we have a similar computation at past null infinity for our in-states and out-states, then the goal for today, so our goal, is to basically demonstrate that there's a ward identity of the following form. Q. S, Q.
Sabrina, it seems like maybe you're
oh no, it's not. Oh god, no. I mean, and this was going good in myself.
We don't see what you're writing. The last thing you wrote is Q plus. We don't see.
Oh no. Okay, can we? Okay, I'm gonna restart my screen share.
Now it appeared.
Oh god. Yeah. Okay, so this weird. Please, do you know? Okay, if you guys have, if you used everything. Okay, so I'll make sure I look up when I write. Good. Like okay. So hopefully, okay. So let's just process what I was. Okay. So let's see, can you see live? Okay, good, now you can see live. So I don't know what, maybe my head is in the way. No, honestly, I don't know why that wasn't, okay. So basically all of the things I was saying before, hopefully were highlighted on the screen at the time, but not your screen. So all I'm drawing right here is this is my future null infinity Cauchy slice. And then this is my past null infinity limit Cauchy slice. And right now I've written down the quantity in terms of data at large R. Fixed u, now u is being sent to past null infinity, so the past limit of future null infinity, so scry plus minus, and this is where this quantity is defined. So the canonical charges for my Cauchy slice are going to be defined on the boundary of that Cauchy slice. That's going to be an S2 sitting near spatial infinity, but we'll get into why it's not actually just trivially, like, so basically what happens is there's going to be a little bit of a non-trivial statement about how to match between the boundary of this past Cauchy slice and the future one. But the goal for today is to basically set up how to get to this ward identity. Also, feel free to like interrupt very quickly because I can't believe I didn't look up when like the whole time. Okay, so as you can tell, me like talking, writing, and then writing and looking up are 3 things to do at once. So definitely interrupt if you think that I am not noticing something. Please do. Okay, great. So now that we're set with our goal. There's one extra ingredient we needed. So what were our ingredients? They're going to be 3. It's written. Good. Okay. So the 3 ingredients are the following. The first one we covered last time, which is this notion of an asymptotic symmetry group. The second ingredient that we're going to need is the notion of the soft theorems. And then the third one is going to be basically an antipodal matching condition, which is the statement I was saying before about how to show that there's a ward identity relating action on the in-states and action on the out-states. So this is going to be antipodal matching. And just to get a sense of the timing of things, essentially this is BMS, so Bondi, Vandenberg, Metzer, and Sachs from the 60s. This is Weinberg, also from around that time, so I think 62 for each of them. And then this is going to be basically like 2013 and 2013, 2014 by Stromander. And that result is basically connecting these two. So we're going to basically have a punchline. Hopefully it's at the end of today that we are connecting these separate stories from the 60s related to asymptotic symmetries that we covered last time and soft theorems that we're going to start with today. Okay, good. So that's the outline for this one. Great. So let us now go to part 1. So today we're focusing on part 2, which is soft theorems. Great. Okay, so the diagram that we're basically thinking of is as follows. We have our outstate, which is basically normally some vacuum and then some creation and operators acting on it for various momenta. So P1, P2, etc. Now, if we look at such a scattering process, so we really don't care what's going on in the middle, we're just looking at our external states. And then we're going to consider the case where one of these guys is the gauge particle and it's soft. So let me draw that here. So I have some outgoing graviton. So this guy is a graviton with momentum q mu. So what I want to say is, so my momentum here is basically going to be omega times reference momentum. So I can write it in terms of the, maybe it's to be consistent with notation that I had earlier, I will write it in terms of the reference direction in that note. P mu equals omega q mu. So there's some reference direction that it's pointing towards, and I have this energy scale, and then I'm going to send omega to 0. So in practice, I'm just saying that I'm specifying something about one of these external states, that there is a scattering process where the out particle, the out set of states included a graviton, and now I'm taking that graviton's energy small. So when I do that, we can look at various contributions that appear in this Feynman diagram, and then hopefully, I think that this is something that you actually do cover in classes, which is nice. I know it's in, like the soft photon case is covered in detail in Weinberg's textbook, but at least in my grad school, they actually spent some time on it, which is nice. Which is the following, is that, okay, so say I start with a line with momentum pi as the out guy. And then I think of the fact that I have now this graviton attaching to one of the external legs. So I'm going to get this extra propagator here, which has momentum pi plus q. Sorry, so in this case, let me just call it q. So yeah, I'll call it p. Q is easier to remember. So I have this extra propagator. And so what this propagator will look like is the following. So basically now I have the following Feynman diagram, where if I imagine, first of all, let's take the simple case where S is 0. So I just have a scalar for the attaching particle. Then the propagator gives me a factor of the following form. So I get pi plus q squared plus mi squared minus I epsilon. And so the point is the following. So I'm sending the energy of this q to 0. Let me just erase any conflicting conventions here. And so what's going to happen now is that basically I can see that this guy is going to be dominated by the term, which is pi dot q. So let's just go through it. So this momenta is basically going to be close to being on shell, or is actually, so this is the outside momenta, so it is on shell. So you have pi squared equals negative mi squared. So what this reduces to is just 2 pi dot q and then minus I epsilon. So if my mass is non-zero, then this guy is never going to be vanishing, so I can drop this I epsilon. Technically speaking, there can be collinear divergences then if the mass is 0. But regardless of the mass of this external hard particle, what I'm going to call it, I have a pole coming from this propagator. And one can see that you're not going to get a similar structure of divergences if you attach to another Feynman diagram. So say, obviously this blob is just representing every other Feynman diagram that you have when you're computing the scattering process. If you have this external leg attaching to one of the like like a loop here, then you're not going to end up having the same divergence, because this divergence is coming from the fact that you have this propagator and this other particle being on shell canceling here. So the leading contribution that's going to happen is when this guy attaches to all the different legs. And so in addition to looking at this propagator, you need to also include the vertex operator, et cetera. But what one ends up finding is that the regardless of the spin of this guy, you end up having the same prefactor up front. So what you get is the following form. You have essentially a soft theorem where I can write it as follows. I have that my out state where this guy now has like no extra graviton. So it's basically the out state that I was considering before minus that soft guy. Then you have a plus minus QS. Okay, let me make sure it's catching up. Great, okay. In equals now this following set of factors. So it's relatively clear how the derivation of this first factor, which is going to be the part that's leading this leading pole in 1 over omega, comes out. But the second one was a more recent derivation by Cachazo and Strominger from 2014. So let's write what these factors are. So the claim is the following, is that this factorization is universal up to these first two terms. And there's even a subleading soft graviton theorem, but the loop corrections for that are not as universal. So what we have right here is the following. So we have, depending, the plus or minus is the different helicities. We have kappa over 2 sum over external states. Assign whether or not the extra particle is in or out, because basically this pi plus q would have a relative sign here if you were attaching to an incoming leg. But for an outgoing graviton, you can attach to any of these external legs. So the sum was over external legs, and we have pi dot epsilon plus minus squared over ei dot q. And then similarly for S1 plus minus, which is this extra order in the subleading soft theorem, we have the result as follows: k kappa over 2, and kappa is the gravitational constant. So kappa corresponds to this like square root of g. So it's 32 pi g. Yeah. Okay. So what we have is the following: I pi mu epsilon plus minus mu nu q lambda j nu, and I can move everything right. Yeah. Great. Okay. Divided by pi. Great. Okay. So what I have right now is I have basically the claim is that what we were showing diagrammatically here is that this guy basically goes like 1 over omega. This guy will go like order omega to the 0. So the contribution that this most easiest to I guess kind of motivate is this leading guy, that it will be a pull in 1 over omega. But one can show that this subleading guy only gets one loop exact corrections. And so at tree level, the form is as follows. And so what one has is the statement here that basically they have both at leading and subleading order a universal factorization theorem of my amplitude. So if I have a scattering amplitude without a graviton, then I have this soft factor where the first factor is just literally a multiplicative factor that depends on the kinematics of each of the external legs. And then that the second guy has some sort of differential operator structure coming from this angular momentum probing the external legs. But otherwise it's also universal. So one thing nice about this.
Sorry, Sabrina.
Oh, yeah.
I forgot what eta was.
Oh, great. Okay, yeah. So sorry, let me write that down. So I kind of said it, but didn't like write it, which is not good. So let's say eta I is basically plus or minus 1, depending if the particle is incoming or outgoing. And so what you can see here is that basically this would be pi plus eta at q, for like eta I equals plus or minus 1. So essentially, right, this has become, if I attached here instead, then this is p, this is q, and then this guy is now right, like p minus q. So
Okay, great. Thank you.
okay, yeah, awesome. Okay, good. So we have that. And now basically what I want to just, I guess, point out is that this is nice and consistent with total momentum and angular momentum conservation. Like obviously we want to use these to talk about asymptotic symmetry, so not just the global symmetries, but the nice way that you can check for the case of the global symmetries is I just send my epsilon plus minus mu nu, which is this tensor product of my spin 1 guys, to what would end up amount to being a gauge shift. So basically these epsilon tensors, of course, are defined modulo the momentum direction. And so when I plug that in, when I substitute this in, one can quickly show that basically one of these pi dots q's is going to cancel the denominator here. And the thing that you're left with in the end will vanish because of total momentum and angular momentum conservation. So in this case, the shift is the following. So these conventions would be such that the energies of the momentum are always positive, so that the eta is the sign for in and out. Versus I sometimes will see in this literature the convention where the P basically has a negative energy sometimes. Okay, so you have that. And then this is total momentum conservation of like, so this goes to 0. And then for S1, you similarly have the following. Eta I epsilon nu q lambda ji the nu. And recall that basically this part here is just some like essentially like a tetrad component, some like projection of the angular momentum tensor, but the fact that total angular momentum is conserved is why this finishes. So already you can see it's consistent at least, which is good. And then the key points for us is basically that if we have a way of essentially extracting the universal powers of omega in this limit from the point of view of what we will care about it being the, I guess, linearized field operator at null infinity. That's going to be the essence of why these are appearing. Okay, so from the point of view of somebody who is studying amplitudes, the first reason maybe why one would care about it is that because, of course, this, in addition to these extra soft theorems that you get when you have a single emission, you're going to have IR divergences coming from loops here. So a lot of the things that we're doing in 4D are nice for various reasons from the asymptotic symmetry side of things, but also kind of indicative of the stickness that you get in the IR limit. So let me add. So when you have obviously soft emissions, you also have all of these particles are charged under the gauge field, which is emitting the soft guy. And so then they're also going to be exchanging gravitons, or if they're electrically charged, photons, etc. So because of that, those exchanges you also need to incorporate. And the IR parts of that are going to give you IR divergences, such that when you sum over all of those exchanges, they exponentiate to basically kill that amplitude. So the typical process, like if you would look at Weinberg's chapter on these soft emissions, it's starting from the soft emission story here and the soft factors. But I guess the big conclusion, I would say, of the way that they phrase that section is that essentially one needs to be careful about the IR observables that one constructs. So a typical resolution is the following, and that would be that you say, okay, so I have a detector. Let me see if I can draw a detector. So I have some sort of detector, and then I have some photon or graviton, whatever, energy deposition into this detector, and I have some cutoff. So I'm not going to see anything below that cutoff. And then when you take into account that anything that you're computing, so when I want to make a prediction, prediction, and add a physical detector, you really need to sum over like what you can observe. So given that point of view, of course, like it makes sense that like your detector won't be able to see infinitesimally like small energies. So from that point of view of like, if I just was like saying my experiment at CERN is going to measure something, but I know that it can't measure below a cutoff, then when I'm doing my Feynman diagram computations, I need to essentially sum over that. And so these virtual emissions in these loops compared to the real emissions that you're not observing kind of cancel that sickness. Now, one thing nice about these asymptotic symmetry story is the following, I guess, point of view and this is also appreciated by others who are looking at dressings like Chung, Fidiev, Kulish, is that basically what we're seeing is we're scattering these states with no soft radiation, right? So when I write down this Fox-based state and I say that I have some vacuum and then these set of definite momentum guys, and they're all actually charged under a gauge field, I'm using the free theory Hamiltonian to talk about like the asymptotic evolution of these states, but in reality, that's not a great assumption because there are long-range interactions. So one way to get around it and one way to guarantee that you're basically going to be large gauge invariant is to include a dressing. So these asymptotic symmetries that we're talking about are intimately connected with these higher divergence issues, essentially because if you were correctly dressing everything, then you would solve the constraint equations in the same way that you would not want to have an electric charge and not have a Coulomb field around it. So essentially, the nice way that informs this discussion is as follows. So there's 2 points in which it informs this discussion. So what are the 2 things we learned? We learned, first thing is this sum over soft can really be thought of as summing over like a state that oh yeah, oh no, okay, good. Wait, that's so funny. So I have to like scroll on my computer to, okay, you see this? Okay, thank you, please call me out, like literally call me out right away, because it's so embarrassing when I'm like, oh, I'm doing better than last time. I have like my like little highlighter and I'm not writing over everything, and then it's like not showing up, like cannot win for losing. So okay. Okay, so now we're at, okay, so there's 3 things we're learning. The first thing is that this inclusive cross-section basically is giving you some state in that sum over soft guys, like it is satisfying the constraint equation. So basically what we're going to have to write down this constraint equation later on, so it's a little bit of a teaser for it, I guess I would say. So, but basically though, like this charge conservation law, or ward identity, basically amounts to like gauge invariance, you could say, I guess. So it's some sort of consistency condition for these large gauge transformations for large gauge in particular. And so basically, like you would see that if you really said like there is literally no radiation, then clearly you'd be violating even what you would understand from classical E&M. So if I were in undergrad looking at, I guess, 807, what I would have is I'd have some accelerating charge. So if I give some kick to my electron or whatever, my like charge Q object, then I know that it's going to radiate. So I have my Coulomb field around it, and then I'm going to get some sort of 1/r radiation when I accelerate. So just that intuition you have classically, the fact that like you know that you have a point charge, and asymptotically it's just the static field, but then if I kick it, there's going to be also a radiative field. If I'm saying that I have some scattering process and there was little or no radiation, one can imagine that'd be a very strange scattering process where all the radiation is emitted and still consistent with those equations of motion, then somehow gets absorbed by the other scatterers. So from the point of view of thinking, like, I guess that classical intuition point of view, one would imagine that it makes sense that when you're scattering, you're saying there's no extra gravitons, no extra photons, you'd get 0. So with that in mind, basically now with this caveat of we're saying that it's an invariance under large gauge transformations, the reason why you need to sum over soft is because you need to include the state with the radiation corresponding to satisfying the constraint equations that we're going to find. So we have that. And then the second intuition that we're going to have, which I guess is slightly funny, is that there's also memory effects. So, I mean, there's still like a sense in which maybe one could further debate the ability to measure 0 frequency, but definitely this kind of detector is not the most general one that you can have. So in this situation, what you're looking at is you're saying that I can only measure below some E cutoff. But to the extent where if you can set up observables where basically you can scale the energy that ever gets deposited down, but have still a finite shift in things. So if one example of that is if I have this boosted point charge, then because essentially my my initial and final kinematics, if I could really say, I'm going to start with one fixed velocity, I'm going to end with another fixed velocity, then you can just look at how the linear record solution has to like induce radiation, and you would see that you should have some sort of shift. So what happens is that basically there are these zero, which we weren't going to really focus on in these lectures, but I do want to point out there's essentially zero modes that you can basically be measured effectively. So they can be measured. And the way that one measures it is basically by looking at net shift. So in the gravitational case, I would have 2-point masses, and they're on some geodesics, and then I have some gravitational radiation passing, and then they're going to get displaced relative to each other. So maybe this isn't the best picture of it. But if I plot basically over time, at early times, there's some separation. Then there's going to be some gravitational radiation moving them around, and then they're going to be displaced relative to each other. And so one could see that, say these, like you can imagine a situation where you don't really have much energy at any given time imparted onto the system, but overall you can still measure this net effect. So it's a little bit of a different setup than this like energy deposition example. And so one would like to really be able to think about quantities where one isn't restricted to computing inclusive quantities. So from these two respects, so from the point of view of large gauge invariance, and then also from the point of view of the fact that these observables are kind of harbingers of these asymptotic symmetries, and we want to think about more than just these inclusive guys, there's kind of two nice things that the story is touching on. Okay, so that's what I want to say about the soft theorem stuff. And so what we're going to need from it basically is just this soft theorem. So this guy here, here is what we need. Good. Okay. So this gets us to step 3. Good. Okay. So now we're on the third out of our 3 steps, where the first step was covered yesterday, and today we just covered step 2. So the third step is going to basically be, how can we combine our definition of Q, our soft theorems, equals basically this semi-classical word identity. How do we do that? So the first thing that we're going to need is maybe why we would expect the word identity to be written in this form. So what I want to point out now is this is going back to our diagram here. So when I have this Q plus and this Q minus, I'm saying that I'm evaluating the canonical charge on either this future Cauchy surface or this past Cauchy surface. And because of the way that gravity is gauge theory, those charges are going to be at the boundary here. So if I want to even like, so say I just ignore the S matrix and I said, okay, so Q plus equals Q minus is basically what this amounts to. To say that Q plus equals Q minus, then I need these guys. So basically, if I put a minus here, basically almost everything looks the same, but it's not trivial that they're related. So the thing that we're going to need is we're going to relate 2 things. We're going to need to relate bonding mass. Let me see if I can do this. Can I copy? How awesome is that? Okay, sorry. I'm like a little bit scale. Perfect. That's great. Okay, so okay, great. So what I basically need to do now is the following: is that I need to motivate to you why I can relate quantities at future null infinity past limit to past null infinity future limit. So let me get rid of. Okay, well, it might be a little bit tricky with not letting me erase certain things, but I'll forgive it. Okay, so what do we have as a bowling? So I have u goes to negative infinity on square plus, and I have v goes to plus infinity on square minus. And so one should be careful, because basically if I'm looking at spatial infinity is spatial infinity for all time, right? So in the same way that typically one would ignore these future, like how I would limit to a null boundary as opposed to just evolving forward in time, one should be careful that if I take r to infinity first, so right, I have basically t equals u plus r. So if I take r to infinity first, you need to take u to negative infinity, and not just negative infinity, but like negative infinity faster than you took r. So in the very strict limit where I'm taking like strictly r to infinity, then I'm essentially still looking at a future amount of time. So one in the exercise, I think it was, hopefully it's the first one of, it's in one of the exercises, hopefully. You get to play with the linear track solution. And there, the kind of intuition for why you have this antipodal matching would be that if I have a point charge and it's boosted, its Coulomb field isn't going to be spherically symmetric anymore. So it would be spherically symmetric in its rest frame, but I boosted it. And the intuition for those solutions is that wherever that point charge is at a given time, the radiation, the radial electric field is kind of pointing towards it. And so one can imagine, like with that intuition, then like at very far in the future, if this guy was headed towards the North Pole, then it's going to be like, so if I draw my Penrose diagram and I draw like kind of the trajectory this guy is on, so maybe I want to avoid Penrose because I want it to be massive, but I don't want it to be massive. So let's kind of draw, like try to draw it a little bit schematic. So there's a bit of a warping from the fact that it's a Penrose diagram, but I'm trying to draw that essentially if I like look at the center of the diagram, that it's heading towards a given direction. So at very future times, then like the particles near the North Pole, if it started out near the South Pole. So that's one way of kind of motivating to yourself, aside from it's easier to just look at the solution and then take the limit Argos infinity first, and then take U versus V to certain values and see its antipodal, which is the point of one of the exercises. But intuitively, you can kind of see from how you would expect solutions to behave on a late time Cauchy slice, that it would make sense that if you wait an infinite amount of time, that at a constant time, this Coulomb solution is going to be basically antipodally related for the charge has been moving forever in one direction. And still there's this order of limits of like, how far has the charge moved from the origin compared to how far you are away from it. And so one can be like confuse themselves there and that, but it's actually a very nice result that was, so I guess a proposal by Strominger. You can see that it's consistent with how the radiation should fall off, that you can try to make sort of matching. But I also in the notes, I put references to more details of how people studying the antipodal matching actually being consistent with, I think, harmonic agent analysis. So, okay. So essentially what I'm going to need is I'm going to have an antipodal matching condition. So basically, antipodal matching like will let me have basically that Q minus equals Q plus in the classical case. So essentially what I'm doing is I'm saying that I have a quantity that's defined here and here, this full S2 around it, and that they're equal, not because they're literally somehow next to each other, because this is an infinite amount of time apart, but because I have like that my solutions will behave in a kind of a manner that respects the CPT symmetry, but also you have to check that it's consistent with the equations of motion. That this guy and this guy are going to be the same values. So typically the way that we do it in this kind of subfield is the way you use coordinates that are already antipodally identified. So then what it will look like is the following. It'll look like CZZ at scri plus minus equals CZZ scri minus plus. And then similarly with MB and the angular momentum aspect. Okay, you can see my change in font, I guess, a little bit live, but the thing here, so basically what I have right now here is that this is the data from the metric appearing in these charges. The other thing that you need is you to match the parameters of the symmetry. And so those will also be basically F is the same at future and past null infinity, and same thing with Y. And it's a good thing to check that the, if I just was in Minkowski space and I did a translation or a rotation, is that matching consistent? And you can check that it is. So basically those are two ingredients. So the metric has to match and the diffeomorphism has to match. And this is important also for understanding the scattering problem, because basically you have, so essentially we have the following pictures that we have a choice of frame, I guess you could call it. I want to say that like I have a choice of like I have a symmetry basically that's going to let me change the value of this zero mode of the metric. And if I could do that independently in the future and the past, it would kind of be sick. So super translation invariance for me is going to preserve that matching condition. And so essentially you have different scattering configurations that are related by the symmetries, but you don't have the configuration where essentially I've started in some configuration and then I've evolved to a different one, because then that wouldn't be a well-defined evolution problem. Because basically I would say, okay, I need to basically specify something happening at spatial infinity in order to do that, essentially, right? You wouldn't want, like the alternative is that I set up a scattering, like I set up my initial data, I scatter, and then I don't know what super translation I'm in, which would be bad. Okay, so this is intimately connected with the well-posedness of your scattering problem, and was an insight by Strominger that you can do this antipodal matching so simply. And let's see now what it gets us. Okay, so the very first thing that we have is basically Q minus equal to Q plus, but that doesn't look like it's word identity, and it looks like the soft theorem that I was talking about. Like, why did I even go through that, right? So the things that we're going to need now is we're going to need the following. So we're going to need, okay, so what we need. Okay, so we're going to need our constraint equations. We're going to need our soft theorem then. And then from there, I think basically, I don't want to include Stokes' theorem as an ingredient, it's fine. So with these two, we're going to be able to show this ASU word identity semi-classically. Because we already have the matching condition. Great. So what we have is the following. So I'm going to do a very simple thing here, which is that I'm going to say that an integral over square plus of u of a u derivative is the boundary values. So okay. So why am I writing down something like that that's relatively mundane is because of the following. So essentially right now at the level of where these charges are defined, okay, so typically what's the data that I think of as knowing on my given Cauchy slice? So if I specify for you this CZZ, then like essentially I'm capturing that when I talk about my outstate for the radiation. So I want to be able to write these conservation laws in terms of data that I would normally think of in terms of my radiative states. So to the extent where I have a detector and it's measuring like gravitons coming out here or photons rather than measuring the Coulomb field at spatial infinity, this is going to be a more convenient way to write it. But in practice, okay, it's literally an identity. So right, so the identity that I have is that integral over here of a derivative is the difference of these two values. So I'm going to also do one little cheat, which I don't need to do, which is that I'm going to assume that it's only massless scattering, so I don't have anything contributing here or here, and that's safe enough to do in the sense that, okay, so like the only thing I'm changing is that I'm measuring the bonding mass and then going to mass spec here. And so I would basically be capturing the late time massive particles trajectory. So it's going to be basically z dependent because of if they're relatively boosted. But if I don't have any massive guys in the outstate, I can essentially ignore it. And I'm basically now able to relate the values here to integrals along here. So in that form, I'm now going to rearrange my Q plus as follows. So what did I have last time? So recall that basically n mu g mu nu, where this is my null normal to null infinity, which for these custom metrics is about this. And there's subletting orders and our corrections to it for the actual like non-flat metric. So I have that. I have my Einstein's equation. So this is equal to T mu nu times that. So those constraint equations that I wrote down last time. And what they give you is the following. So maybe I'll write down the bonding mass one for the sake of not everything being confusing. So hopefully this was last time. I have that du of the bonding mass equals 1/4 dz squared du czz plus dz bar squared du c bar minus tu. And where I not cheated, but I did take a kind of quick route where basically this guy is the matter tu plus like terms that are like nzz, where I'm being a little bit schematic with the factors here. So essentially the reason why I'm separating out is as follows. So from the point of view of, okay, so if I wanted to even just look at like what, if I wanted to represent this like symmetry transformation here, these quadratic terms are going to have like a dagger and a in it. So basically preserving the particle number. So in the given state, it's going to measure the energy for you. Versus what these guys have a flavor of it. So like the linear term is special because it's basically going to act inhomogeneously on the vacuum. So for the purpose of, obviously like this term being here is very important. If I wanted to study a pure gravitational theory, the fact that I can have some sort of notion of a memory effect without having other sources there is really interesting. And I don't want to undermine that or by like kind of hiding it in here. But from the point of view of trying to study spontaneous symmetry breaking dynamics, this guy is the part that's linear in the metric, and also the part where my energy is going to be going to zero because, right, if I send this, so this dn here is this guy, so it's du of czz. So I can send this guy to be small but have a non-trivial integral, and it will basically send this term to zero. So this is a bit of a different flavor. This is like the memory effect type of observable I was talking about, as opposed to this guy being the energy imparted by the gravitational radiation is small. So this is my constraint equation. And all I'm doing right now is I'm basically plugging it into this Q as I've written it here. So if I was only looking at super translations, this is all I would need. I say, okay, the bonding mass here, I'm going to write it as a integral of a U derivative. And then I'm just going to basically be able to plug in this term here. So I'm going to write out what the charge looks like for, I think I wrote it for both. Okay, I might have only read it for one. Okay. So I'm going to write it out for the subleading self guide, because that one is the more interesting one from the point of view of celestial CFT at the moment. If anything, there's something kind of where the leading one will confuse it a little bit, and then you have to go back and understand it, because essentially what happens is that when you make the boosts front and center, translations look funny because they're shifting you off of the light cone. So because of that, even though it's a more complicated transformation right now, or manipulation right now, it'll pay off for not kind of confusing the intuition. So I'll do that. So what do I have? So basically plugging this in, I have my Q plus now written as a U integral as follows. Phi G, integral now over all of square plus, not just square plus minus, of this guy. And then, yeah, gotta love I can actually move things now. Okay. Times 1/2 dz cubed yz u du czz plus yz tuz, and this is the same type of trick as I was drawing for the matter uu component, dz yz u tuu. Okay, so what I have here is the following. So right, basically as I was claiming is, okay, so this constraint equation isn't that bad. There's a similar one for the England domestic, which I'm also using here. Now I have what I was hoping to have, which is I have this U integral over my radiation field. So in this case, this is the graviton will be appearing here if I promote this to an operator. So I'm going to promote it to an operator. And then for this guy, it basically is measuring the energy momentum of the other hard particles. So I'm going to call this quantity here Q soft, the full integrated quantity. And then this guy is going to be called Q hard. So what do I have? This Q hard guy, because I'm saying that it's basically, the stress tensor is measuring, essentially, it's like it's doing the motion, the diffeomorphism on the hard matter. So what I have is the following relation for the hard charge. I would have, my state is labeled by some energy and some position, some momentum direction. So it's position on the social sphere, but right now it's just momentum direction. Q hard plus is going to be I y dzk plus 1/2 dzk k, so ck omega k d omega k. Okay, so what I have right now is the following. So this is coming from the fact that basically I'm looking at the momentum space version of implementing the Lie derivative of my momentum direction along the vector field here. And the reason why I would do that is because essentially this is a stress tensor, right? So it's the current for doing those, the diffeomorphism in my field theory. On the other hand, this guy, I need to use my soft theorem to evaluate. So for this guy right here, I can essentially plug in my C hat ZZ as I had before, and then do this U integral. So hopefully I wrote it down last time, but definitely in the section that we reviewed quickly, we had the following statement. We had that the saddle point approximation was giving me essentially the ability to interpret the large R limit as localizing the momentum direction towards that point in the celestial sphere. So what I had before, and I'll write it now in terms of C because we've introduced the metric since then, is that I have C ZZ is basically proportional to, so the proportionality factor doesn't matter right now. I mean, it matters for plugging it in, but it doesn't matter for the sake of explaining where it's coming from. Even I omega C bar U, and then HC. So there's an I over. Okay. So what I'm saying right now is the following. Essentially what's happening here, right, is that at the stage of just doing the large R approximation, so this is coming from the large R limit. So this is from R goes to infinity, U fixed. So because I took that limit, I landed myself on basically the direction on the night sky. So the direction at null infinity of this momentum is matched, but I still have this omega integral. So what am I doing here? What I'm doing, this U integral basically, this U integral here is going to pick out a zero mode here. And so one can see that this, depending on the operator that's appearing here, so the powers of U, if there's U derivative or whatnot, then I'll basically be selecting out different orders in omega. So what you can check is that you can check that this guy is projecting out the leading pole and only giving me the subleading soft theorem. So essentially, the way that this ward identity works right here is that, okay, so what I have, I show that this hard charge, because the stress tensor is generating the symmetry transformations of my matter fields, is giving me this. And now you can show that the same quantity with the right appropriate sign to make it all sum to zero is coming from this guy, with the important caveat as follows. So Q soft right now was coming from a either outgoing graviton or an incoming graviton, and those guys attached to all in or outgoing external legs. Whereas this hard matter charge is acting on my Cauchy slice either at future or past null infinity and is only contributing from one or the other. So essentially what I basically have is that you need both terms to have this ward identity work, but you do have it work out. And so basically I've shown how one lands at our word identity. Are there any questions at that point? I mean, hopefully the ingredients aren't too separated out. Because that's kind of that's the punchline for this section 3. Modulo, one other thing I want to say if I have a chance. How am I doing in time?
You have 10 minutes.
Oh, perfect. Okay, so great. So hopefully, if that's understandable, there's one punchline that is basically going to then set us up for the next part of the lectures, which is, I guess, the more interesting thing for Amplitudes people. So it's going to be good. So basically, like why are we going to CCFD? Right, we have this symmetry, this symmetry. So super rotation symmetry. We're basically 2 copies of the Witt algebra. So if we look at the central extension, you have a Virasoro. So right now we have essentially from the space-time point of view, okay, so we have asymptotic symmetries that correspond to the subleading soft theorem that give us this Virasoro symmetry of the celestial sphere, and they were called super rotations. But right now, we've done everything in position space, we've done everything with our energy eigenstates right here. And the whole point is that we don't just care about the fact that we have this symmetry, it's more also that like manner in which we can write the word identity is reminiscent also of this 2D CFT. So right, so let's see what we have right now. So we have in 4D versus in 2D. So from the 4D point of view, we have these super rotations. And the symmetry looks like these CKVs, so conformal killing vectors on this celestial sphere, but we can just say this is some 2D project like plane or Riemann sphere embedded in this light cone of 4D. So we have the same symmetries on both sides. Now, these guys corresponded to word identities for asymptotic symmetries. So they basically had soft theorems were equivalent to like word identities for ASG, for this ASG in particular. So this asymptotic symmetry. And so normally in this 2D CFT context, we would have a stress tensor giving me the word identity. So word identity. So the beautiful thing about the story is not that you have the same symmetries, but that you also have a candidate for what this guy is. And what it ends up being is that basically this guy becomes equivalent to QSoft. So what did we really have before? So in this side of the story, we had QSoft and QHard, where basically QHard was doing the transformations on each of the operators, each of the external states. Let me not jump the gun here. So this guy gave the delta for each like external state. And in this situation, normally you would have the stress tensor insertion, then giving you a bunch of reversal symmetric transformations of my external operators. So my O delta J. So what I want to be able to do is I want to be able to write down a map between external states and O delta and J, which is, I guess, the one that I teased at the beginning. So external states mapped to a delta J, and in particular local operator in my, sorry, let me write that. Local operator in my CFT, and O delta J of bar. Good. So let me put that here instead of the, where is it? So this is what I want. And then in particular, I have that this stress tensor guy that I would have in the 2D CFT is equal to this QSoft for a particular value. So my QSoft was a function of Y. If I take Y to be 2I over Z minus W, then I get me my candidate stress tensor. So essentially what happens is that we've gone through this process where at the time, all we wanted to show that super rotations were a symmetry of scattering. So the whole point of this derivation, which is like with Capets and Lysov and Andy, is that we were just interested in whether or not these proposals for asymptotic symmetries were going to be realizable or somehow like we're already a symmetry of the S matrix as it's normally formulated. And so we used the soft theorem to show that this symmetry proposal was useful. So okay, so like I guess from the point of view of the Y, Bondi, Vandenberg, Metzer, and Sachs were excluding super rotations because they weren't acting globally on this celestial sphere. So because they'd have funny punctures, it didn't seem, there's a natural way to kind of exclude it from the symmetries of these metrics, because you can say, oh, you don't want any metrics of singularities, okay, they're gone. But when you have then the S matrix and you see that because of these soft theorems, you do have a way to write them as being invariant under these symmetries, and it's reasonable to include them. So our point of view was that we had this new soft theorem from Picasso and Strominger, which was inspired by these questions about whether or not there'd be an extension of the rotational part of the symmetry group. And then that proof was to show, okay, yes, we have that effect. So at that stage, we're essentially sticking to this 4D story, where we just wanted to motivate that there was this asymptotic symmetry. And we knew then that there was this 2D CFT interpretation of those symmetries. So that's good. But the really nice result by Ray Claroux and others with Andy is that basically this guy gives you a value of this stress tensor. So essentially the form that we have is that this QSoft and QHard, the way that QSoft will shift the vacuum and then QHard shifts the operators, is the same structure that you'd have in the CFT. And so generally you have this story, which we're going to set up as follows. So this is going to be the teaser for next time. So we're going to see that we have this part of the map. So this is part one. And then the second thing that we have is we're going to have that for special delta and J, we're going to get currents. So we have, sorry, currents. So we have soft charges in 4D become currents in 2D. And if anything, this part of the story is actually the thing that was most like developed ahead of time. And so really motivating this map for all energies is going to be the where we start off next time. And then we come back to this and it's going to be fun. So that's where we're at right now. And this is a good teaser for the lectures tomorrow and the next day. So I'd like to, I guess, stop there, and hopefully I was okay with timing. And any questions? So yeah, so I also let me know if the exercises seem aimed appropriately to whoever is.
So it seems Stefano's connection is